So let's do a little reviewing for the second semester final. Electric field, it says right here, electric field is 80 newtons per coulomb. That's E, capital E for electric field. What is the force is what it should say, so that's a question. And we're given this for something charge, charge. So that's Q is the abbreviation for charge. And you have to remember that micro is 10 to the minus 6. So what's the formula for that? Electric field equals force per charge. That's a Newton per coulomb for electric field. So they give me the value of E, and we're looking for F, and we know this is 4 times 10 to the negative 6, and that's what you plug into your calculator. You're going to cross multiply to get a force of 3.2 times 10 to the minus 4 units are newtons, named after Sir Isaac. All right, here we have two charges separated by 2 meters. What's the electric force, and is it attractive or repulsive? Okay, so there's 2 charges and a distance. That's always my clue to use a famous formula called Coulomb's law. F equals K Q1 Q2. It's the only formula with 2 charges in it, divided by D squared. K is a constant, it's given, so you don't have to memorize it, but it's 9 times 10 to the 9th. And now I'm going to plug in my 2 charges, 0.02 and 0.05. And I'm going to divide by the distance squared. That's one place people make some mistakes, so don't forget to square it. And then it's plugging and chugging to get your final answer of 2,250,000 newtons. That's such a huge number. So what it points out is that these are very big charges. Even though they're fractions of a coulomb, that's still a lot of charge to have in one place. Attractive or repulsive? Well, I'm making a big assumption here, and it's not really that big of an assumption, I guess. These are both positive values. It's not explicitly stated, but if they're both positive, then they repel. Negatives repel negatives, positives repel positives. It's only opposites that attract, Paula Abdul. All right, when you have resistors in series, they simply add up. It's the easiest way to add, and literally I'm just going to take 24 ohms plus 24 ohms to get 48 ohms. If I had 4 or 5 or 6, I'd just add them straight away like that. So that's your answer if they're in series. In parallel, you have to add them inversely. Remember, the formula is 1 over the total equals 1 over the individual resistors added up. If I had 3, I'd just keep going more and more and more. Not hard to do on paper, especially if they already start with the same denominator, because that's the only way you can add fractions, is when they have a common denominator. So that's 2/24. That's not your answer. I have to invert both sides. That's 1 over the answer. So if I invert this fraction to make it R total, I have to invert this fraction to make it 24 over 2, or 12 ohms. And remember, on your calculator you can also do this. You can just do 24x to the minus 1 plus 24x to the minus 1 equals, and that would actually give you, here I'll do it real quick, 0.083333. That's not your answer. Hit x to the minus 1 one more time, enter, that gives you your answer. All right, this starts with a little multiple choice test. Do I use the word if the voltage through a 6 ohm resistor, or if the voltage across a 6 ohm resistor? Okay, voltage is always placed across something. It's a potential difference. And how much current flows through it, or how much current is across it? Current, like a river, flows through things. So now you could read the whole problem. If the voltage through a 6 ohm resistor is 24 volts, how much current? All right, one of the most famous equations in all of physics, and one of the most important for the exam, is Ohm's law. V is voltage. It's measured in units of volts, so that's why I know it's 24. I is current. That's what I'm looking for. R is resistance measured in ohms, so that's a 6, and that's pretty easy math. For capital A for amps or amperes. You can say either one, amps or amperes. All right, so let's look at this one. This one also is Ohm's law. The only tricky thing here is you can't just put a 3 in, can you? It's got to be 3 times 10 to the, let's see, milli is -3. And kilo or killa, what's that one? 10 to the positive 3 for those of you watching this at home. Oh, this is nice though, because what happens with 10 to the -3 and 10 to the +3? Works out to be 10 to the 0. What's 10 to the 0? 1. So while I say they cancel and even draw lines through them and cancel them out myself, remember that they really multiply to make 1. So in other words, we can drop them, leaving us with 18 volts. So it's kind of a cool thing to write. V equals 18V. Yeah, that makes sense to a physicist or an electrical engineer. Next one, hair dryers rated at watt. What's that W stand for? No, that's what I'm asking. Watt? Oh, all right, bad joke. So, watts is a unit of power. Capital P, power. And here's another V for voltage. Actually, that V is for volts, and I'll label it V for voltage. How much current flows? All right, so my first question is I equals question mark. Are you looking on your formula sheet? What relates P, V, and I? You see it there? You got it. Power equals, I think it's written IV on the formula sheet. And so we have 1800 equals I times 120. And I is 15 amps. I just want to take a brief detour here and point to this number. You don't have to be given this number. It is totally fair of your teachers to expect you to know that if it's plugged into a household circuit, a typical household circuit in the United States, that that's the number you plug in for V. You should know that as a learned person of science. Second half of the problem, though, what's the resistance? Well, to relate resistance to all this, I'd go right back to George Simon Ohm's law. I've got my 120. I just calculated that this was 15. Solve for R. Eight ohms. How's that, Holmes? Oh, this one, love it because it's got a trick in it. And it's a fair trick. Do you know what the trick is here? Bat sends out a sound wave, bounces off something, comes back in 0.2 seconds. How far away is it? This is how bats navigate, echolocation. If you want to break it down in terms of simple physics, all you're given is a time here. T equals 0.2 seconds, and you're asked to find out how far away. That's a D equals question mark. So right away you ought to be thinking of a very simple equation. V equals D over T. But if you use that equation just as it is, you don't get the right answer. What's the trick to this? For any echo problem, what do you have to add to this formula? You've got to put a 2 in front of the D. Because the sound wave goes out. Let me see if I can draw a bat super fast here. Here's my bat. Sends out a sound wave, hits something out here, right? And part of that sound wave comes back. It goes there a distance D, and then it comes back a distance D. It's just traveled 2D. And there is another little trick. We don't have a speed for this problem. But anytime you're given a problem like this in air, you always use 340. Hey, this class knows their stuff. So it's 340 equals 2d over the time given, 0.2 seconds. So on your calculator, you do 340 times 0.2, divide by 2. You can do it all at once if you're good with your algebra, to get a distance of 34 meters. Nice work. A wave has a frequency of 34 hertz and a wavelength of 2 meters. What's the wave speed? Now, don't get carried away. This is not a wave in air necessarily. You don't know that. So don't assume that it's 340 here. This is leading you to the wave equation. The wave equation relates, sorry, a little technical difficulty. The wave equation relates frequency and wavelength to speed. And I'm sure once I write it, you'll all remember V equals lambda. And we're solving for V, so this becomes pretty straightforward. This is 34 hertz. This is 2 meters, 68 meters per second. That seems pretty simple. Period and frequency. Ooh. First thing you got to remember is, how do you label period? Look at the units here. It's got units of time. Right? See these units here? But you don't want to give it a lowercase t. You give it a capital T. Capital T is 4 seconds. So the relationship between frequency and period is inversely related, just like that. So if it's 4 seconds, the frequency is 1/4, or 0.25 hertz is maybe the other way to write it with a decimal, 0.25 hertz. If the frequency is 200, what's the period? Well, we can just reverse that inversion. I don't even know if that makes sense. And write it that way. Period is 1 over f. And if it's 1 over 200, you could leave your answer as a fraction, or that's 0.005 seconds. Next. Now here, we're back to what's the wavelength of 170 hertz sound wave in air. Okay, so we're back to air. So at least in air, I know the speed is 340. It looks like we're going to do another calculation for water. So I know the speed, wavelength, that's that funny lambda, lowercase lambda symbol, is a question mark. Let me just move that over here. Wavelength equals question mark. And hertz, what's that again? Frequency. Okay, right back to the wave equation. But we're going to do it twice. We're going to do it once for air. And get 2 meters. And then we're going to do it again for water. What do you think is going to happen to the wavelength in water? Well, the speed goes way up, right? It's 5 times the speed. Does the frequency change when you go into water? Nope, frequency never changes once it leaves the source. So you're going to get 8.8 meters. Yeah, it's not quite 5 times the speed. Good, but speed goes up. If the speed increases, wavelength increases, because they're directly related, directly proportional. All right, so here we're given a time of 10 seconds, and we want to know how far away it is, distance. One thing we're missing is speed, right? Because I need speed to relate distance to time, but it's air. And we always assume that if we're not given a temperature, we're going to use 340. Do I need a 2D up here? Nope, I don't, because the lightning strikes over here, hits the ground, and that sound wave just travels some distance to get to you. It's not bouncing off of anything and coming back. It's just distance. All right, so easy peasy, 3,400 meters. Don't I need to account for how long it takes the light to get from the lightning to me? I could if I wanted to be really picky. I could do a V equals D over T calculation for the light. Technically it would be C equals distance. Whoops, I know the distance. 3,400 meters over time. I could compute this because I know what C is. It's always the same, 3 times 10 to the 8th meters per second. But if I take 3,400 and divide by 3 times 10 to the 8th, I'm going to get 0.00013 seconds. All right, well, that's good. So what's 10 minus 0.000013? Still rounds off to about 10 seconds. Yeah, so the light gets there virtually instantaneously, certainly at this distance. All right. If the frequency of the second harmonic is, what's the frequency of the fourth harmonic? There's really 2 ways to do it. Take 5 seconds to think about how you do it. And I'll show you the foolproof method, and maybe you saw the shortcut to this one. The foolproof method is finding the fundamental frequency. Remember that the second harmonic is equal to twice the fundamental frequency. The third harmonic is equal to 3 times the fundamental. The 182nd harmonic is equal to 180 times the fundamental. And they tell me that the second harmonic has a frequency of 300 hertz. Can you find the fundamental frequency? Absolutely. I'm just going to divide 300 by 2 to find out that the fundamental frequency is 150. This subscript 1 represents fundamental. This subscript 2 represents the second harmonic. Well, now it's easy because I know that the fourth harmonic, represented by that subscript 4, is simply equal to 4 times the fundamental frequency. That's 4 times 150, or 600 hertz. But you may have seen the shortcut. Did anyone see another way to do this? Did anyone recognize that the fourth harmonic would always be equal to twice the second harmonic? That's always true. Like, what would be 4 times the third harmonic? Which harmonic would that actually be? The 12th harmonic, right? It always works that way. If you ever see it, take the shortcut. Aha! How many times more intense is 60 dB compared to 30 dB? There's a rule here. And the rule is that for every 10 dB step, the intensity gets multiplied by 10. So 30 to 40 to 50 to 60, every one of these steps from 30 to 40, I need to multiply the intensity by 10. And I'm going to multiply by 10 again. And I'm going to multiply by 10 again. In other words, I'm going to wind up with an intensity that is 1,000 times greater. The rule for loudness is, whoops, I forgot a B in here. Let me just add that back in. The rule for loudness is that for every 10 dB step, it's about twice as loud. So let me just write that out again real quick. 10, 20, sorry, starting at 30. 30, 40, 50. Although it never really matters where you start, it's always about how many steps you take to get to the final spot. So that is loudness times 2. But then I'm going to multiply by 2 again, and multiply by 2 again, and wind up with a final answer of 8 times louder. Whoa, I got a lot of space to do a simple problem. Because do you remember the relationship between focal length, and radius of curvature? The radius of curvature is equal to twice the focal length. So this becomes really easy. And that formula should be on your sheet there. It's just 2 times 12, 24 centimeters. All right, in terms of math, I think these are maybe the most challenging, just because they're 2 steps. So, how tall is the image? That's an HI kind of question. And you could try starting with a formula with HI in it, but you'll run into a roadblock, and you'll have to, somewhere along the line, use this equation. So since I've seen this a few times, and hopefully so have you, you kind of know to start with this equation. And 12 is the focal length. I don't know what DI is. I don't know where the image is going to wind up. They tell me the object is 20 centimeters in front of it, so that's a positive 20. And now I can solve for DI. Remember the trick to do this on your calculator? It's 12x to the minus 1 minus 20x to the minus 1. Might not be a bad time to practice real quick. But that gives me like 0.03 repeating. Aha, because that's not the answer. You got to hit x to the minus 1 one more time. Enter. DI is 30 centimeters. Well, that's great, but I still don't know what HI is, except now you can find it with the other equation for lenses and mirrors. Hi, ho, negative di, do. That's what will allow us to do it. So I got HI is my unknown. HO is 8. That's up in the problem. Now I know this is 30. 20 was always given. And I'm going to get 12 centimeters for my answer. It's, whoops, and I forgot something, didn't I? It's negative 12. Do you know what the negative sign means? It's inverted. And it also means it's real, because those two words always go together. All right, I think we just have a couple left. Oh, little technical glitch here on the slide. Looks like the degrees didn't come through. All right, so a beam of light goes from water to plexiglass. I'm just going to sketch that out super fast. Remember, we measure everything from the normal, so 35 degrees would be like here maybe. And this is 35 degrees. It's water, so this is 1.33, and this is plexiglass 1.50. And just right now, you should have an idea of what that refracted ray looks like, where it winds up. Is it closer to the normal, further from the normal? Have an idea in your mind. And let's do the math. Snell's law. So it's n I sine theta I, or I think on the formula sheet it's 1, and then N2, or NR, whatever you want to subscript them as, theta R. All right, so I'm in the water to begin with. That's the 1.33, and I'm given that incident angle of 35. And R is given, that's the plexiglass, and I need to find the other angle. And in class, I can hear people punching buttons furiously already. I'll do the same. So I find that the sine of the refracted angle is 0.508 and a bunch more decimals. I take the inverse sine of that, literally second sine, inverse sine, then second answer if you're working on your calculator, to get 31 degrees. Rounded to the nearest whole number, it's 31 degrees. So it bends slightly toward the normal to make this my 31 degree angle. How come it doesn't bend very much? Because look at these two numbers. They're pretty close to each other. They're not a lot different, right? In fact, if they were exactly the same, what would happen here in the picture? It would just go straight through. No bending whatsoever. Are we up to the last one? Or that was the last one? Bonus question in physics. Here it is. What's the magnification of the image given all that other stuff? Magnification. So I know that formula. That's either high over ho or negative di over dou. Well, it's 2 steps to find hi. It's only 1 step to find di. That's the way I'm going. Heck yes. All right, so I'm going to do my 1 over f equals 1 over do. You could do it the other way. It's just going to a little bit longer. I'm going to take the shortest route possible. Focal length, 10. do, 30. I'm getting those from the problem. And di is unknown. Don't use 12 anywhere. That's the height. I don't want that in this formula. So again, 1/10 minus 1/30, and then invert that. So you should have 0.06666. Invert that to get 15 for a di. And now I'm practically done. My magnification is equal to the opposite of 15 over 30. My magnification is negative 0.5. What's the negative mean? It's inverted, which would also tell me it's real. You got it. Nice work. And smaller, the 0.5, right, tells me that it's smaller.